The purpose of an arc flash hazard analysis is to determine how much energy would be released if an arc flash were to occur. Once those calculations are performed, safe work procedures can be developed and proper protection can be chosen based on the hazard level. On average, an arc flash analysis takes 6 to 12 weeks to complete, depending on several factors. Variables such as the size of the facility, number of utility services, number of electrical components, and the condition of the electrical distribution system and protective devices must be taken into account. The entire electrical distribution system does not necessarily need to be studied during an arc flash hazard assessment. In this section, we will review how to do an arc flash analysis or study. How do we determine the amount of energy that is released if an arc flash accident happened? After discussing the energies released during an arc flash and witnessing footage of arc flash incidents, it is clear why OSHA, CSA Z1000, CSA Z462, and NFPA are so invested in preventing arc flash hazards. The final piece of the puzzle is determining how to protect workers from suffering injury in the event an arc flash does occur. OSHA addresses the need for hazard identification. 1. Identify the hazard. 2. Eliminate the hazard if possible. 3. Provide safe work procedures for the hazard. 4. Provide proper personal protection equipment. And 5. Train qualified personnel on safe work procedures and personal protection equipment. The reason to perform the study is to identify hazards so that we can put safe work procedures in place and we know the appropriate PPE to wear. This is what directs our training of qualified personnel. Arc flash hazard analysis is a multi-step process. 1. Identify points where calculations need to be made. 2. Data collection. 3. Electrical maintenance. It is highly recommended that there be energized or de-energized maintenance during the data collection in order to ensure that the equipment is in safe operating condition. 4. Manufacture and install labels. These labels will tell us the arc flash energy and where to set up our arc flash protection boundaries. 5. Select personal protection equipment. 6. Electrical safety arc flash training of personnel. Point count. The first step, point count, uses a one-line diagram to identify where calculations need to be performed throughout the electrical distribution system. The one-line drawing in this video uses red arrows to indicate which points require calculations. This process is also useful because it helps estimate the time and cost associated with the arc flash hazard assessment. Notice we use a simple one-line diagram. We have a utility service, a main breaker in the switchgear with its bus and several output devices. You'll notice we are feeding a motor control center, a distribution switchboard, a step-down transformer, a motor load, an industrial control panel, adjustable speed drive, and UPS and battery system. We also have an automatic transfer switch and an engine generator. Data collection. Data collection is the second step in the arc flash hazard analysis and refers to the gathering of all the information needed to make the calculations. This is a very detailed process, but is crucial to the accuracy of the entire analysis. Here we have listed the various pieces of information needed from the electric utility that supplies your facility. Phase to ground fault current, phase to phase fault current, impedances, conductor lengths, types of insulations used, type of transformer, and type of cooling. After this information is collected, it is entered into the engineering software used for the calculations. We move forward to our main circuit breaker and collect information such as manufacturer, the breaker model number, the trip unit model number, and the plug model number. There are typically 4 settings on the trip unit that need to be recorded. We need to identify the size of the switchgear bus, which is shown here in red. What is the bus length? What are the bus dimensions? What is the amperage rating? The voltage rating? As we move further into the system, we have highlighted the output means of disconnect. They may be circuit breakers, as shown here, or fuse disconnects. We must record the manufacturer, the model number, the type of trip unit and model number, the trip unit settings, the current transformers. If there are fuses, we need to determine what is the model and the type, and what is the amperage rating. Finally, in our examples, we need to look at the feed conductors. From those output devices, we need to determine what are their lengths, what is the insulation type, what type of conduit is being used, what type of bus is being used, and we need to know the size, length, and amperage rating are important. As we continue further into the system, there are some very particular items we are interested in. With respect to the step-down transformer, we want to know its kVA rating, what is its load, what is its maximum load, what are the tap settings, what is the impedance, how is it cooled. Motors are also a special consideration during the data collection process. We must determine the arc flash energy available when the motor is open and energized, as well as the amount of energy a motor can contribute to an arc flash event. When an arc flash event occurs, the motor may actually become a generator. Inertia will cause the motor to continue rotating, feeding voltage and amperage back into the electrical distribution system. This will increase the length and intensity of an arc flash event. If there are a large number of motors, less than 50 horsepower, they should be considered one motor. For example, if there are 10 motors within a motor control center, they should be added together and treated as one 400 horsepower motor. There are other special locations we need to address: UPS and batteries, engine generators, and automatic transfer switches. Once again, we need to determine what arc flash energy is available, as well as the energy these devices feed back into an arc flash event. Consider an engine generator. When an arc flash event occurs, a single phase to ground or 3-phase fault, the ATS sees a drop in voltage and will start the generator. The generator will come online in approximately 10 seconds. Next, the generator will feed the fault and will only turn off based upon the time setting of the breaker at the generator. We need to calculate how it will backfeed during an arc flash. Engineering. The third step in the arc flash assessment process is engineering. There are 3 main components to this process: fault current calculations, coordination study, and the arc flash incident energy calculation. All 3 are crucial to ensuring accurate results. Here notice both the blue and red areas on our simplified one-line diagram. The blue indicates where fault current is examined throughout the facility. The red is the coordination to show when the breakers will turn off if we have a 3-phase fault or a single-phase fault. Remember that fault current refers to the amount of current flowing from a piece of equipment. This is measured in kA, or tens of thousands of amps. We start with the utility service and examine how it propagates through the distribution system. The coordination study deals with the breakers and determines how much time elapses before the breakers de-energize the equipment. Fault current, or short circuit study, and coordination study calculations have to be performed first before we can move to our arc flash calculations. Once these calculations are completed, a label is created. A label is generated for each point where the calculations were performed. Here is a sample warning label from a previous job with number 3 in the top left. This stands for Hazard Risk Category 3, which indicates that the clothing that the qualified person is to wear is 25 calories per centimeter squared. This label also shows the shock boundary distances, or the arc flash protection boundary distances. This is where we set our boundary before we open up the equipment. It tells us when we need to wear insulated gloves and insulated tools, which we do in this case. We need to wear a full hood with a face shield and a hard hat that is integrated into it. The label tells us we need to wear eye protection, which is required underneath the face shield. This is the information generated from this three-step calculation process. This label now goes on the piece of equipment that it was calculated for and becomes our work procedure regarding PPE. Now let's discuss training. Training is a requirement every time we develop safe work procedures and recommend PPE. We are required by OSHA to train those people exposed to that hazard in the use of the PPE and in the use of the safe work procedures. This is classroom or hands-on training and can be held at the customer's site. The training can range from 1 to 3 days to review the following: arc flash incident energy warning labels, levels of incident energy calculated at each point on the electrical system, flash protection or approach boundaries, required PPE at each location where an arc flash label is installed. Keep in mind that this training is very important and must be completed. Once the arc flash study is done and the labels are installed, then it is time to purchase PPE. Based upon the installed arc flash labels, you may need to purchase everyday FR shirts and pants, helmets, face shields, and insulated gloves, FR overalls, flash suits, and arc flash hoods, insulated tools or blankets, and boundary equipment for establishing flash protection boundaries. These labels tell us exactly what PPE to purchase. OSHA also tells us that each worker must be properly fitted, which means that PPE is purchased not only to meet the label requirements, but for each qualified worker as well.